This lecture is on electricity and human body. The nervous system of the human body is made up of trillions of neurons, which are actually the nerve cells. Inside and outside the neuron are electrically charged particles like sodium, potassium, calcium, etc., which go in and out through the cell membrane. This movement is required for nerve cells to communicate with each other. Now, if an electric current of sufficient magnitude is conducted through the body, the effect of this electric current interferes with the biological electrical activity within the body, and this interference disrupts the proper natural electrical pattern and can also create serious consequences. So in this lecture, we'll see an overview of these impacts of the electric current. Now, if you take the electric current, the severity of an electric current through the body depends on three main factors as shown here, which are actually the current magnitude, the duration of the current, and the path through the body. Now, the current magnitude, the larger the magnitude, obviously, the larger will be the impact produced inside the body. And the current magnitude actually depends upon voltage, frequency, and the body impedance. Higher the voltage, higher will be the current magnitude for a given impedance as per Ohm's law. And frequency has an impact as well, which you'll see later, and of course the body impedance. So if for a given value of voltage, the current and the impedance are inversely proportional to each other, once again based on the Ohm's law. So lesser the body impedance, the higher will be the current flowing through the body for a given voltage. Now, the current magnitude, depending on the magnitude of this current, a person may experience an electric shock or an electrocution. So the electrocution is again higher the magnitude of current, it leads to the death of the person. And sometimes higher magnitude of current may also cause external and internal body burns. So the point where the current enters the body, there may be a burn, and similarly the point the current leaves the body, there's a burn externally. And internally, the path through which the current flows through the body, the tissues burn up. So the magnitude of the current impacts the amount of tissue burning as well. Now, if you take the duration of the current flow, the extent of damage produced depends on this duration. So for longer duration of the current, the higher will be the impact. So even though the magnitude may be small, if the duration of the current is large, the impact created will be larger. Now, the duration actually creates the burning effect on the body. So this is given by I squared here, T here, because we know that the heat produced is given by I squared R. Now, if we assume the body resistance is constant, so the heating produced in the body due to the shock current depends upon the square of the current and the time through which the current passes through the body, because power times the time taken gives you the energy. So that's the energy effect. Now, path through the body, obviously the current may take a different path depending upon the point of contact with the energized object and the point through which the current comes out. So in this particular figure here, you can see the person is touching with his hand, touching the energized object with his hand. So the current flows, enters here, flows, in this case it looks like it flows through the heart, and then it leaves through the feet because the person is touching a grounded floor. So the current flows through the heart in this case. So obviously whenever the current flows through nerve centers and vital organs, the shock effect is severe and it can lead to the death of the person. Now, the next one is the physiological response of the body to electric currents. Now there are different ranges given here. The physiological response of the body depends on both magnitude and duration, but let's see only the magnitude effect here. Now up to 1 milliampere, you can see less than 1 milliamp, there is just a faint tingle, and this is called the perception level of the current. So up to 1 milliamp, there is not a big impact, only a faint tingle. This value in reality varies with the conditions of the contact. For example, when the contact is made, the conditions may be dry or wet, and the pressure of, if the person is holding the energized object with a high pressure, that is tightly, then the impact may be larger. And the area of the body in touch with the live parts, whether the contact is made just with a fingertip or with a complete palm, or the fingers wrapped around the energized object, and the physiology of the individual, in the sense, what is the impedance of the individual. Every person may have a different values, but then the general range, all these values are calculated for male adults. So the general range is 1 milliampere. So 1 milliampere is a perception level, which means above, the shock effect is felt only above this perception level. Now the next threshold we have is 10 milliampere. So up to 10 milliampere, the person holding the electrodes can let go of the electrodes, which means the disturbance produced in the nervous system is just a transient condition, and the nervous system, there are already, we saw there are already ions inside the body, and the ions are subjected to a transient condition, but this settles down quite quickly. This is called the threshold of let go, which is 10 milliamperes, and again it applies for adult males. The next level is a current of above 10 milliampere. Okay, now for a current of about 10 milliampere along the nerves, it can order the muscle fibers to mechanically contract. After the contraction, the muscle slowly returns to the resting state. However, if this current continues to flow, the resulting contraction of the muscle is maintained as a constant spasm. The injured therefore cannot let go of the energized part that he or she is in contact with, and when the current stops flowing, the muscle slowly expands towards the resting state. So therefore, this range is actually called the threshold where the person cannot let go. So it's inability to let go. The next level is if a current is greater than 15 milliampere, so 15 to 100 milliampere here. So this may lead to the paralysis of the respiratory muscles, causing a difficulty to breathe or irreparable brain damages. So in this range there is difficulty with the breathing. Above 100 milliampere, so this range we are talking about, it produces what is called the ventricular fibrillation. So above 100 milliamperes, ventricular fibrillation occurs, so during which the cardiac muscle disorderly contracts, denying the proper blood circulation, which is crucial to supply oxygen to the body. So this is considered to be the main cause of death in the case of electrocution. Now above 100 milliampere, for example, if the current magnitude, although it's greater, if it flows for a very short duration of time, the person could still survive when the current is 500 milliampere, but there are respiratory problems occurring, but the heart restarts when the current stops. Now there are also different ranges here, up to 6 ampere and above 6 ampere. So obviously in these cases there are serious burns, there could be respiratory paralysis. So again, this does not mean that the person can always survive. for a higher current. But if the duration of the current is quite small, they may survive, but that leads to serious burns or respiratory paralysis. The electric shock. So the electric shock occurs when human body becomes a conductor. Okay, so the current passing through the human body from an energized object causes the electric shock. This is often referred to as the macro shock. So it's called a macro shock. So we have already seen that the effects of shock depends on the current magnitude. However, the magnitude of the current depends on the impedance offered by the body and also the applied voltage. For example, in this particular case here, the person is touching a faulty equipment. So you can see here the ground pin is missing. So therefore, when the equipment is faulty, the current, rather than passing through the ground, the fault current, it passes through the body of the person and the earth, because the human body offers a very low resistance. So you can see here the resistance offered by the human body is just 1000 ohms. So obviously the current chooses the path of very low resistance rather than the actual conductors, which could offer a higher resistance. So in this case, the voltage applied is 120 volts. So the current through the body therefore is just Ohm's law, 120 volts divided by the human body impedance, which is 1000. So there is a 120 milliampere current. So based on the discussions we had previously, 120 milliampere is above the range of ventricular fibrillation. So this person could be subjected to an electrocution rather than a shock, which means there are lots of chances for ventricular fibrillation. Now imagine this is 120 volts, a US system. If you take an Australian standard voltage, it's 240 volts. So the current flowing through the body with 1000 ohms resistance will be 240 milliampere, much higher. So this is how the electric current through the body is highly dangerous. Now the effects of shock. So apart from the standard ventricular fibrillation and inability to let go, and therefore the burns, there are other effects caused by the electric shock. So if we talk about the direct effects, we know it causes pain, involuntary muscular contraction, there could be paralysis, ventricular fibrillation of the heart, and of course the burning. These are all direct effects which I have already seen. Now other than this, even if a person gets a shock, he may not feel anything. There may be a pain and then he may think that he's all right, but then things could happen internally and this will lead to a number of indirect effects. There could be confusion, amnesia developed later, headaches. Often we may get headaches, breathing problems, heart irregularities that may occur now and then. So the problems may last several days, and there could be vision abnormalities, swelling of the affected areas, and long range effects. There could be speech, writing impairment, loss of taste, and other disorders occurring. So internal injuries could occur as well. So there could be internal bleeding, tissue destruction, which may not be immediately apparent. So this is very important. So left untreated, they may cause death. So the figure here shows a person working at a height. So when such a person is subjected to electric shock, there may be problems not directly by electric shock, but the person may fall over from heights due to loss of balance immediately after getting a shock, and he may also experience, if the shock currents are greater, he may experience muscular contraction, which again leads to other problems, and he may fall down and even die. The figure here shows the impact of burns due to shocks. So see here, this shock is due to a process, something called an arc flash or the arc blast, and you can see here this is when the electric current enters the skin at this point. This is the electric current when it exits the skin. So you can see there are burns externally produced when the current enters and exits. So imagine internally the tissue would experience burning as well. So the circulation of the electric current through the tissues, let us say the current through the tissues is given by I, and let us say it passes for a time delta t. The duration for which the current flows is delta t. Now this generates heat. So what is the heat of the current? We know that the heat produced is given by the power, which is I squared R, and the energy, when you take the energy, we can multiply by the time. So I squared R delta T gives the energy produced due to the current passing through the tissues. And you know that the resistance R is given by rho L on S, where rho is the resistivity, L is the length of the tissue, and S is the area of cross section of the tissue. So additionally, let us also assume that there is no thermal exchange between the body and the surrounding environment. That means the heat is not dissipated, the heat inside the tissues. So in this case, all the heat developed by the current is absorbed in the tissues. So what happens when the current is absorbed? The temperature of the tissue rises. The heat accumulated in the tissues can be given by this expression, where S is the C is the specific heat capacity of the tissue, okay, and then delta theta represents the difference between the initial temperature at the inception of the current through the tissue and the final temperature after the time delta t. Okay, so once again S is the cross sectional area of the tissue. So therefore we see that the heat effect produced is equal to the heat absorbed in the tissues. So rewriting this one, we can write delta C is given by I on S the whole squared, rho on C delta T. So I on S is the current divided by the surface area, which is J. Okay, so which is called the current density. So we can see that the rise in temperature to which the human tissue is subjected depends upon the square of the current density and also the duration of the current circulation. So square of the current density and the duration of current circulating through the body. If the area of contact is sufficiently large, because we know that J is given by I on S. So if the area of contact is sufficiently large, J is low enough, and that will not damage the tissues even if the current is of high value. So that's the impact of shock currents on the burns. So even if the current is of larger magnitude, if the surface area of the tissue, the cross-sectional area of the tissue is large enough, then it may not produce a sufficient impact in the body. Now the ELEC9716 describes the effects of the AC current on human when it is subject to a left hand to feet contact. So this is a shock current zone as prescribed by ELEC9716. Again, the assumption made here is the person is subjected to a left hand to feet contact. So that he is touching the energized object with the left hand, the current leaves through the feet to the ground. So these curves do not take into consideration the individual size and also identify 4 current zones here. So we have current zone 1, AC2, zone 2, zone 3 and zone 4. So it identifies 4 different zones. So what's the significance of these zones? So if we take zone 1 here, you can see it's a straight line. So there is a straight line here at 0.5 milliampere. So the x-axis represents the current in milliamperes and y-axis represents the duration of the current in millisecond. In zone 1, the persistence of the current is possible, but there are no reaction. It has an upper limit of 0.5 milliampere, and in this zone there is no sensation at all. So the current up to 0.5 milliampere, there is no reaction. Now coming to the zone 2, in this zone you know that the current range is 0.5 to approximately 400 milliampere for small timer, and you can see here there is a slanting line, which means for higher ranges of time, if the current duration increases, duration of the current increases, the range gets narrower here. So maximum is only 5 milliampere here. Whereas if the duration of the current is smaller, you have up to 500 milliampere. So in zone 2, the involuntary muscular contractions are likely, but there are no harmful effects. In this zone, there is a prickling sensation and possibly painful effect on the muscles, especially in fingers and arms. So overall, there is no harmful effect. Now let's go into zone 3. So in zone 3, the reactions are usually reversible, but there are strong muscular contractions. Although once the current stops, the muscles will get back to normal. In this zone, there may be respiratory difficulties, a temporary cardiac arrest, but there is no ventricular fibrillation. From 5 milliamperes, so you can see upper range varies from 5 milliamperes with a duration of 5 seconds to 10 seconds here, and up to 200 milliamperes or nearly 400 milliampere with the duration of 10 milliseconds. So the currents are quite painful. Now the next zone is zone 4. So in zone 4, this is a zone which produces ventricular fibrillation. So the probability of this ventricular fibrillation increases with the magnitude and the duration of the current. For example, there are 3 different zones in 4. Zone 4.1. So in zone 4.1, there is up to 5% probability of fibrillation. So it is up to 5%. And the next is zone 4.2. In zone 4.2, there is a probability of up to 15% chance for ventricular fibrillation, and in 4.3, the probability of fibrillation is greater than 50%. Now in this time zone, you can see that the curves here take a bend. So there is a bend here, sharp bend in these curves. So which means it exhibits a sudden change somewhere in the midsection. So these curves are almost vertical, either above 1000 milliseconds. So here it is almost vertical above 1000 milliseconds, or below 200 milliseconds they are again vertical, but there is a change only in this section. So what's the reason for this change? This is basically due to the behavior of the heart. When shock currents flow through the body, the heart beats faster than normal because the tissues are subjected to all changes, ions, movement within the body is disturbed. So therefore the heart starts beating faster than normal. The chances of ventricular fibrillation also increases dramatically when the shock duration exceeds 1 heartbeat. That's why for longer durations, as seen here, the ventricular fibrillation chances are more. So that's why the shape suddenly changes in this region. Let's now see the effect of frequency on the shock. So let's consider two waveforms, waveform 1 and waveform 2. So you can see here the frequency 1 is greater than frequency of 2. So by comparison we can now find that the time periods of the first curve T1 is less than T2. So T1 has a lesser time period. If you can see here, this is the time period when compared to T2. So this is T1 and this is T2 time period. So that's the first curve is present for lesser number. T1 is lesser than T2, which means the magnitude remains positive for a lesser number of time for the first curve than for the second curve. So which means the stimuli due to the first curve may not go beyond the excitation threshold of the nerve cell because of its lower application time. Thus we can say that high frequency currents are therefore less dangerous. So it passes through, you can see here high frequency means it very often crosses the zero. So therefore high frequency currents are less dangerous than the low frequency ones of the same intensity. So which means although they have the same maximum value, they are less dangerous, which means again we can conclude that high frequency may not cause ventricular fibrillation, but of course currents, all high magnitude currents always lead to tissue burns. Similarly, the effect of very low frequency is also minimal, because when we have a very low frequency, the stimuli is not long enough, and the prolonged stimulus caused by the low frequency, if you take for example the low frequency is the time period is greater. So for low frequency, let's say F low frequency, that leads to longer time. Okay, so that leads to longer time. So because the time of application is quite longer for the low frequency, the prolonged stimulus effect is produced, and this causes the nerve cell excitability threshold to increase. So overall it increases because it takes a longer time between one stimulus and the other stimulus. Therefore the effect of very low frequency is also lesser. That's why if we can see this curve, the low frequency effect is lesser, high frequency effect is lesser, and if this is for the safety factor, so the safety factor is minimum in this range, which is unfortunately 50-60 Hertz current. So 50-60 Hertz current, which is the normal one used throughout the world, is the most dangerous current. Now when you see the effects of DC, by the same argument we had as before, for very low frequency, DC is therefore generally less dangerous, since the shock thresholds are significantly higher for DC than for AC. For example, for AC we know that the threshold of perception is 2 milliampere for AC, whereas the same threshold of this is for AC it is 0.5 milliampere. The threshold of perception is 0.5 milliampere for AC, and for DC that becomes 2 milliampere. So the threshold of perception is much higher for DC than for AC. Again, if you draw the curve here with time along the x-axis and current along the milli-axis, you can see here this is AC, these three curves are for AC, and these three curves are for DC. Now if you compare these two curves, you can see here the DC current remains at a higher value until the time of contact is 200 milliampere. So which means for lower duration of the current, DC is more dangerous, and for higher duration of current, AC is more dangerous. So this can be seen from these curves. So these are actually the fibrillation curves.